Hey, good morning, everyone. Today we will try to get into all of the circuits that we will need for lab next week. So I'm going to do something a little different. What I'm going to do is this. We have several diode circuits that we will perform experiments on the next couple of weeks. So what I want to do is we'll do ideal diode analysis on all of these diode circuits so that students are better prepared for the lab. And then we'll come back and look at the equations and the terms, the quantitative stuff next week. Okay, so today we'll do the description, the qualitative description, and then next week we'll look at all the equations of the quantitative. Okay, so first up is diode rectifiers. Oh, before I do that, in the homework, the first problem is about diode resistance and so let me write this down here. There was VD0. VD0, the equation is diode voltage VD minus the thermal voltage VT. VT, of course, is K times T over charge Q. Chapter 2. K is Boltzmann's constant, T is the thermal temperature in Kelvin, and Q is the charge. And then diode resistance RD from Ohm's law, VT over ID. Okay, these are the two equations you will need for that homework problem, which I guess I shouldn't have assumed that students would read the section. So I should have stated that. It's in the assigned reading. Yes, question. It does. It's in the book. Yes. RD. D. Robert Downey Jr. So the theory is, so let me explain it quick. So question is about RD. So the theory is basically that you have this diode characteristic, right? And the Q point may be anywhere along the characteristic. Okay. So wherever the Q point might be, we'll treat that as a linear portion of the diode characteristic. Or all the characteristic is nonlinear, but certain pieces, if you break it up, it is linear. And so the Q point, wherever that might be, we will draw a linear line that will intersect the x-axis. And that intersection point right there. Yeah. And then that's where it's come from. That's where it comes from. But so section 3.10.1 or 2 in the book. Yes, partial derivative actually. Which is an important question. What do you call that symbol here in the US? I asked a couple of people, but they tell. In India, you know what I'm talking about? Partial derivative operator. Apparently on the internet, when I looked it up, they say it could be like a funky D or a funny D, but it's kind of like a italicized version of that. We learned it as DABA. I don't know. It's interesting. Different parts of the world, we learn the same things, but we refer to it differently. Anyway, so that's what you would need to solve question number 1. All right, so let's go into diode rectifier. So the lab next week, you will, and I'll get back to that multiple diodes again next week. Lab next week is about half-wave rectifiers, full-wave rectifiers, diode clippers, and clampers. And then we have Zener diode the week after that. So what I will do is I will cover rectifiers today. I'll also try and wrap clippers and clampers, the qualitative description. not the quantitative equations. Okay. And then next week, we'll look at the equations, the analysis using multiple diodes, using the ideal diode model. And then I'll also cover a little bit of the Zener diode next week. And so that way we are in tune with the lab, okay, in time with the lab. It doesn't help that the lab is earlier in the week. Most, or at least 3 of my sections are earlier in the week. Okay, half-wave rectifier. Now, the diode, as simple and as humble as it might be, it's a very important electronic device. A lot of the foundation of electronic devices that we use today are based on the operating principle of the diode, or are actively using the diode. Okay, it is actively used to shape an AC signal. Okay, so far we have considered diodes by only applying a DC voltage or a DC current, and then determining where the Q point or the operating point might be. From this point on, we will look at diodes with AC as well as DC signal, meaning we would apply a DC signal perhaps and see how the diode, we'll apply a DC signal to bias the diode at a certain point, and then apply an AC signal on top to see how it would deal with it. And so it modifies the AC signal, meaning it's shaping the wave or shaping the waveform. Hence, these circuits are also known as diode wave shaping circuits. Okay, diode wave shaping circuits. First one up is the diode rectifier. Simple circuit with a single diode and a single load resistor. Okay. What we are doing here is we are directly applying a time varying AC signal to a diode. Okay. So this is right here, the AC input signal. And what we will use to analyze this is the ideal diode model. Okay, ideal diode model. I would also like to state at this point, in chapters 1 and 2, we dealt with atomic structure, movement of electrons and holes. And then earlier this week, I stated that we are now into circuit analysis, like actual circuits, right? So we were zoomed into the atomic structure, so to speak. Now we are zooming out. Now we are looking at the diode as a component as a whole. Okay. So while you try to understand this material, while you try to understand the circuit analysis, I always strongly recommend to students, understand what the circuit is doing first, use the diode as a building block. Okay. Once you understand that, then you can zoom back in and try to figure out, what is exactly happening at the physics level, meaning the electrons and the holes and the movement of those. But first step is to actually understand how the circuit is working. If we don't understand that, then we cannot, that's the foundation, basically. That's what I'm trying to say. So don't get too bogged down in trying to understand the flow of electrons and holes at this point. Let's put a pin on it and leave it to the side for a bit. So in the ideal diode model, you only have 2 states. Diode is either on or off, right? So don't worry about diode voltage, the turn on voltage, nothing else except the 2 states. Positive voltage, it's on. Negative voltage, it's off, right? So this is if anode has a voltage that is higher than the cathode, and off is when anode is less than cathode. So when we perform these analyses, these techniques, first thing you want to identify is what is the voltage at the anode and the cathode. Okay. And then you make a assumption on whether the diode is on or off. So let's begin. If this is our AC input and we are applying it to this diode right here, It's applying both positive as well as negative, right? So let's take it 1/2 cycle. This is the positive half cycle where the voltage is positive. So during the positive half cycle, diode D1 is, I hear on from this side, on, right? So positive half cycle, D1 is on, it is conducting. And if it's conducting, it is essentially allowing everything that is coming through exactly and passing it through the output, exactly as it is, no modification, right? Ideal diode, meaning it's a short circuit. If it's a short circuit, then the positive half cycle is going to allow whatever value is coming through to proceed to the output without any modification. So V out would be equal to V in. And this is positive half cycle, positive half. Let's take a pause. You write it down. Let me know if you have any questions. So far, so good. Negative half cycle, it reverses polarity. So there are many ways to display that. I usually just turn the source around. Or you could keep the source the same and say it's a minus voltage being applied. But turning the source around makes it easy. It's a negative half cycle, is an open circuit. VO is equal to 0. Output goes to 0. Nothing reaches the output. Okay. And so the waveform is a flat line at 0. And so replicate it exactly as it is. Actually, on, off. You see why I don't like grid lines on graphs? That's why I'm always insistent. If you have to have grid lines, make them faint. So on during the positive half cycle and off during the negative. Does that make sense? Right? That essentially is the complete working of a half-wave rectifier. Let's take the two terms. Rectifier. Rectify means it is converting AC to DC. Just in the normal sense of the word, rectify means you have a problem, you're solving it. That's what it means, right? In this case, it's not a problem as much. We just says we want DC, but we have AC. So we are rectifying the AC to DC, we are converting. So in this case, in this sense, rectifying simply means converting. So you're converting AC to DC. Next is half wave. It's quite evident, only half of the input signal is being converted to DC, right? Only one half. Negative half is gone, it's wasted. And then finally, the question would be, how is this AC? Isn't it time varying? And the answer is correct. Yeah, it is time varying. So it's not fully DC, right? But it's just moving in one positive direction. So I would say it's somewhere between AC and DC. I like to call it personally a pseudo DC. But we have to think of it in terms of the average value. Okay. So the average value of this waveform if you were to think of this as mountains of dirt, and then flatten them out, that level would be the average DC value. Okay, so even though this is a time varying signal, we still refer to it as a DC value or a DC signal. This is basically the first step in converting AC to DC. There are a few other things and components that we add to get, like a flat line. Make sense? Right, let's take a pause. Let me know if you have any questions. Or just, yes. Why? He's hesitant. Why is he hesitant? Exactly, yes. The point being made is if you wish to obtain a flatter line, we add a capacitor. The answer is correct. By the way, do students see this in physics classes at all before anything? No, right? Okay. Well, that's true, yeah. You haven't even seen diodes in physics. This is the first time, right, for diodes and everything. Yeah. Where? Oh, right here. That's a good question. I don't know. 1.014. I'll have to check my notes. Oh, yeah, that's the 0.318 times 5 volts. So the average value of the DC voltage. Okay, but we'll look at that next week. That's the average value. So it would be somewhere here. That's 2.5, so maybe somewhere here, I would say. That's another learning moment of why when we use graphs and images, our information should be on there with visual cues. So just a number by itself doesn't make any sense. We should have a notation somewhere in there, like an average line or something. Okay, any questions on this before I move on? Okay, so then, actually, yeah, let's talk about the transformers. Since you brought it up. So in the lab, we used to use the function generators, okay, in the function generators. But because all the instruments are grounded, we can't find an instrument with floating ground anymore. Almost no one makes them anymore. Since the instrument is grounded, the negative end of the supplies of all our instruments, like function generators and oscilloscopes, everything is grounded. So if you try to apply a signal to a half-wave rectifier or any rectifier for that matter, the other end is going to be connected to ground. And we won't be able to use it. We won't be able to see the waveform on the oscilloscope. So now we have gone back to the future in that sense, old school. We are now using actual transformers in the lab. And so actual transformers, which I know for a fact that you have studied in 212, right? So this is a step down transformer. The step down transformer. And it takes the 110, 120 volts from the power outlet and steps it down to, I believe, 12 volts, 12 volts AC. And again, those, that's how an actual DC power supply works. Even today, the devices that we use, the chargers that you plug into the wall, or your mobile phones, your tablets, your laptops, they still function on this exact principle. You have a transformer at the front end that steps down the voltage. It's either now modern smart phone chargers, they are rectified first, then they're converted back to AC and stepped. So it's a little different. The standard chargers that we had available until just about a decade ago, they all had a transformer right at the front end. You plug it into the wall, it steps it down, and then you rectify it. Okay. That will look next. So half-wave rectifiers, of course, you're losing a lot of the energy. So how to make most use of the waveform at the input? Well, one of the ways to do that was using a center tapped transformer. So this transformer would actually have a tapping in the secondary winding. Tapping simply meant you have a primary coil, you have a primary coil, you have a secondary coil, and all you're doing is somewhere in the middle of the coil, you're taking an output. You're tapping into it. So it's basically as if you have multiple secondary windings. It actually is wound around the same core. You're simply pulling an extension out. You're pulling a contact out. That's the simplest way to look at it. And I believe this is also something they would have seen in magnetic circuits, right? So I still remember when I was a student, I had we had variable power supplies. And so those variable power supplies would have multiple tappings in the secondary coil. And so each one of those would result in a different voltage, like 1.5 volts, 3 volts, 6, 9, 12, 15 volts. And so depending on where you're tapping the secondary coil, the amount of voltage that is appearing changes. But in a center tap transformer, what we do is, let me draw a better diagram. Okay. You have two diodes. The way to draw this is both of them are pointing towards the right or away from the secondary coil. And that's it. That's the secondary part. So when you tap into the transformer, it acts as two independent supplies for those two diodes. Okay. So you have D1 and you have D2. And that's your load resistor in the middle. If you notice, it's the exact same circuit, right? The ground symbol indicates everything with that symbol is connected together. That's all it means. And so that would be this point right here on the left near the tap. Let's take a pause while you write it down. Yes. So in this example, so the question being asked is how would that transformer work, or how does a tapping work, right? Tapping is basically you're just taking an output in there. So you're splitting the secondary coil into two parts. Now, and that depends on the number of turns and the turns ratio and all of that. So it depends on what output we want. In this case, we are simply saying that it's the secondary coil is divided in exactly half. But if you wish to, let's say, as I said, the variable power supply that I used to have, the primary input was 220 volts, Asia, and then the output was 15, 12, 9, 6, 4, 6, and then 3, and then 1.5. So depending on what output voltage you want, the number of turns would be different. So it was not exactly center tap. Center tap, by its very definition, means you're tapping into the center of the secondary coil. So you have equal voltage in both halves. But in real life, again, depending on your use case scenario, you would be tapping, differently. The whole point is that the turns ratio should be different. Okay, so the way this would work is exactly the same. In the positive half cycle, positive half, your center tab looks like this. Okay. You have a positive here and a negative here, a positive here and a negative here. So your diode D1 is on and D2 is off. Again, ideal diode model. So positive is being applied to D1 and negative is applied to D2. So your circuit looks like this. And the current is, of course, flowing in this direction, entering the resistor from the right. And so the voltage drop across the resistor would be plus, minus. So D1 is on and D2 is off. So it's behaving like a half-wave rectifier. So positive half cycle, diode D1 is on. So you would obtain, and let's D1 on. And then negative half cycle, polarity reverses. And so we would obtain D1 off and D2 on. And it would look like this. Plus minus, and the current is now flowing in this direction. Let's take a pause, write it down, think over it, and prepare your questions. So what do you think? All right. Positive half cycle, center tap transformer, plus at the top, minus at the bottom. Same thing applies. The beauty of the transformer is that the same appears at every coil. And so if you have a center tap transformer and you have two diodes in there, one diode will be on for one half cycle, the other one will be on for the other half cycle. So now, excuse me, now we are making full use of both half cycles of the AC input. So positive half cycle, D1 is a short because it's on, D2 is off, so it's an open circuit. Negative half cycle, D2 is a short and D1 is an open circuit. In both cases, the current, of course, is going from plus to minus. In both cases, the current is entering the resistor from the right, as shown in our diagram, as illustrated in our diagram. So it's going from right to left. Point of entry is towards the right, so the voltage drop across the resistor is in the same direction for both half cycles. And that's the key point. Okay, the voltage drop across the resistor, the current flow through the resistor is in the same direction in both half cycles. And thus, we obtain a waveform that looks like this. I still missed the mark. All right, let's try again. So here D1 is on, here D2 is on, here D1 is on, here D2 is on. Okay. And so we have a full wave rectified output, hence a full wave rectifier. And because we're using a center tap transformer, it's a center tap full wave rectifier. And center tap rectifier also has some limitations, chiefly that we have to use a transformer that will be more expensive than others. You'd have to use a center tap transformer, multiple windings. All right, questions? Make sense so far? Yes. Like the output or the input? Yes. Well, that's the operating principle of using a filter capacitor, but it's not in the frequency. So tying this to real life scenarios, most parts of the world, 220 volts, North America, 110 volts. That's the frequency you want to rectify. So it's a very, very low frequency. So, but the point that you make is valid. If it's a very high frequency, you can place a capacitor in there. The point would be that if it's a very high frequency, the capacitor could be very small. But if it's 110 volts, which is what our purpose would be, the capacitor has to be very large. Typical power supplies, I've seen capacitors like, the wall warts that I was talking about, 10,000 microfarads, like really big. So 10,000 microfarads is what, 10 millifarads or 0.01 farad. So really big capacitors, capacity. Yeah. And since you're on the topic of capacitors, let's talk about the filtering a little bit. So you have a capacitor connected at the output in parallel with the resistor. So I'm hesitant to throw a lot all at the same time, but let's you have this waveform that's coming in, right, at the output. Okay, look at the, so I'm talking about this image right here. So you have this waveform that's coming in. Capacitor is connected across the output. The same output is going to the resistor and is going to the capacitor. Okay, capacitor starts charging. Okay, reaches full charge. Then the cycle reverses, goes negative. Capacitor is charged in one direction, so it's now trying to discharge. But the capacitor is large in size. The size of the bucket is huge. If you only have a small tap at the bottom, it takes a long time to drain all of that energy. And so, because of the size of the capacitor, it's slowly discharging. Before it can discharge fully, if we stop the AC supply, at some point the capacitor will reach zero. But before it can discharge completely, the next positive half cycle arrives, and now it starts charging again. Then goes negative, starts discharging, again at a very slow rate, and then charging, and the cycle continues. And we have an almost flat line. Okay, almost flat line. This right here is known as the ripple. It's like a wave ripple, right? And hence it is known as the ripple. The actual DC component, of course, is, and I'll draw the waveform down here. Actually, you know what? Let me use the same one that I use here. So if we applied a capacitor, and let's say it's somewhere here, so it would charge. The first one would charge, discharge. It starts discharging like this, charging, discharging, charging, discharging. Okay. And so this is the ripple. The actual DC voltage would be somewhere, you would average out the ripple, of course. And this would be the total DC voltage because it's almost like a flat line. And by obviously, when we design it in such a way that the ripple is as small as possible. Compared to the DC output, the ripple is like in millivolts. And we add one more thing to it, which is like a Zener diode. So Zener diode will hold the voltage completely constant. So again, as I said, like a true power supply will have like multiple components. Okay, so that's what is a ripple. And because the capacitor is removing the fluctuations in the voltage. It is known as filtering, and so the capacitor is also known as a filter capacitor. Okay, filter capacitor. And so let's see, full wave rectifier center tap with a filter capacitor, because it's filtering out the ripples in the waveform. All right, let's take a pause. Questions? It's 8:46. All good? Okay. Then we come to the standard bridge rectifier, right? This is pretty much what is used in all power supplies. Okay, no need for using a center tap. You seem to be very excited. So, full wave bridge rectifier does not require any sort of tapping of the transformer. You simply have a transformer, step down transformer, and you use 4 diodes instead of 2 to obtain full wave rectification. The easiest way to draw this circuit is like this. You make 4 points in the shape of a diamond. And let me spread this out a little bit. Then you take 2 of these points and draw 2 of the diodes pointing up. That's what I like to call it. 2 diodes pointing up, and the other 2 point down. And that's it. 2 pointing up, 2 pointing down. And then take 5 seconds and look at the diagram. What do you see in terms of terminals, in terms of the anodes and the cathodes? So there are 2 terminals where the 2 anodes meet, and there are 2 terminals where the 2 cathodes meet. And there are 2 terminals where there's an anode and a cathode. Where there are 2 dissimilar terminals is where you would apply your input. And where there are the 2 similar terminals is where you would take your output. And so you would connect your resistor or your load right here, where the 2 anodes meet and the 2 cathodes meet. That's where you're taking the output. And where the anode and cathode are meeting is where you're connecting your input. And so this is where we would supply our input. Okay. So again, 4 dots, make 2 diodes pointing up, 2 pointing down. And then once you have your rectifier circuit, you should ensure that you have 2 anodes and 2 cathodes, and then 1 anode, 1 cathode at 2 terminals. And that's how you know your rectifier diagram is correct. Okay. Let's take a look at how this would work. So I'm going to name this, actually, and I'll use the same naming, D1, D2, D3, and D4, counterclockwise. Clockwise. So in the positive half cycle, this is what's going to happen. We have, screen went off. Okay. I'm going to draw it out a little bit large, that plus and a minus here. And this is going to be a little tricky, but here it goes. You have an anode here. Don't draw this out. There's a purpose. So this is for explanation purpose. You got positive being applied here, and you have a negative applied here. Which ones are on and which ones are off? So positive at the top, negative at the bottom. So this is where I was saying, don't zoom in too much. Take like a 10,000 foot view. If there's positive at the anode, meaning the anode is higher than the cathode, then the diode is anode is p-type. If p-type is connected to positive, diode is on. Whereas negative, diode is off. So the diode D2 and diode D4 are on, and D1 and D3 are off. Take a few seconds, and I'll repeat. There's positive at the top, negative at the bottom. So positive is being applied to D1 and D2. D1 is a cathode, D2 is the anode. So D2 is on, D1 is off. At the lower half, negative is being applied to the cathode of D4 and the anode of D3. Hence, D3 is off and D4 is on. And so the circuit's going to behave like this. The short here. And there's a short here, which allows, let's do this, current to flow in this direction, causing a voltage drop with a positive on the right and negative on the left. So this is D2, this is D4. And I will write D1 is off. Actually, D1 and D3 are off, and D2 and D4 are on. Okay. So there are two of them are on, two of them are off. Make sense? Oh, we're running out of time. And the negative half cycle, the exact opposite happens. Now D1 and D3 are on, and D2 and D4 are off. And so top, bottom, and now this is on D1 and D3. And the current now is going in this direction. It is the exact same direction as the positive half cycle, and it still causes voltage drop in the exact same. And again, that the key point, current is flowing in the exact same direction. So voltage drop in both half cycles is same, plus on the left, minus on the right. And this one is, let's see, what is this one? D1, and this is D3. And so you again get a full wave rectified output. So here it's D2 and D4 on, here it's D1 and D3 without without the need of a specialized tapped transformer. Okay. All right, let's take a pause. Questions? This is pretty much every wall wart had inside it. And, when it's very easy to make. So I've seen, like, I had, again, going back in the day, decades ago, I had seen devices where they open it up and they'll simply be like diodes, like twisted around, just like, bare twist. And then, a few months later, you realize why it's not working anymore because something is shorted out. But again, saving on cost, making like a cheap power supply and just getting it out the door. So that's how they used to do it. They still do it for some things inside speakers. Just have components mounted on top of the speaker without a circuit board or any kind of wiring. But that's a full wave bridge rectifier. And again, the filtering applies the same as what we discussed. You have a rectified AC output, and you apply or you connect a capacitor in parallel with the output resistor. When you connect a capacitor, starts charging, then the negative half cycle, it starts discharging, but the size of the capacitor is so huge that it takes a very long time for it to discharge. Before it drops even like 10%, next cycle arrives, it starts charging again, discharge, charge, discharge. And so it's almost like a flat line. And so this is something we'll look at next week. We have like 3 minutes left. Let's diode clippers. Not enough time to go too in depth, but clippers and clampers are two circuits where diodes are used to clip the output of the output waveform. Okay, and the circuit, of course, should be familiar because it's similar to a half-wave rectifier. A half-wave rectifier clips the negative waveform, right? Clips the negative waveform, negative half cycle. And so a half-wave rectifier behaves like a diode clipper. So diode clippers are used to clip the waveform or the output at a certain level. That level could be, well, depending on the use case scenario, the level could be anything. Okay, but it's used to clip the output waveform. It's 8:59. So let's not rush into anything. I'll cover this on Monday. Let's do that. Can devote 1 minute of time left to any questions that you may have. Covering clippers and clampers on Monday will still be before Tuesday, so that's good. All right, any questions? Go back and review this if you have time, like right now. Might spend like 10 minutes just reviewing it if you wish, just so that it sinks in. But definitely review it later on, at least during the weekend. Okay. We'll end class here today. If you have any questions, still have 10 minutes before the next section begins. Quiz as usual on Monday on the work that we have learned this week. Okay. So it'll be diode analysis using the techniques that we have learned. Maybe ideal diode model, constant voltage drop model, iterative analysis, mathematical model, load line analysis. I haven't decided yet. Maybe that will be the take home portion. I don't know. Yeah. All right. I'll bid you all a good weekend. I will see you on Monday.